So good morning, everybody. So this is a little summary just to recap where we stopped yesterday and also where we started from. So the idea was to introduce this problem of landscapes by this setting of inference or denoising. So we were considering denoising problems for matrices of this form, where J here was chosen to be a matrix taken from this Gaussian orthogonal ensemble. And this matrix is spiked, so it is perturbed by a signal here, which is, if you want, a rank 1 projection in the direction of some vector, and this vector V lives somewhere on the sphere. And I remind you that the idea was to find a way to gain some information on the position of this vector on the sphere. So what we did yesterday was to introduce these ideas of maximum likelihood, and we saw that this maximum likelihood estimation could be mapped into a problem of optimization for a landscape that is high-dimensional. So the landscape here is simply the quadratic form which is associated to the matrix that you want to denoise, and it is defined on the sphere, which has a radius square root of n. So the idea of maximum likelihood is to find the ground state of this landscape, and then we discuss some more general questions and realize that somehow we are not only interested in the ground state, but also in the structure of the landscape on top of the ground state. So are there many local minima, and what are their properties? And starting from here, we mapped this back into a problem of matrices. So we saw that if we are able to compute the spectrum of the matrix M, so all the eigenvalues and the eigenvectors, then this will give us all the information that we need for fixed realization of this random landscape. So all the stationary points are in 1-to-1, actually in 2-to-1 correspondence with the eigenvectors associated to the matrix M. The energy density of this stationary point, you can read it if you know what is the eigenvalue associated to the given eigenvector. And we were also asking questions about stability, and this is somehow encoded in this quantity, which is the index, so the number of negative eigenvalues of the Hessian matrix around the stationary points. And this is also encoded in this labeling alpha. So the idea is that if you look at the eigenvalue that has position alpha, if I order them this way, then the index is simply given by n minus alpha. So this tells you that for all possible choices of alpha, you have saddles. So you have at least one direction where the curvature of your landscape is negative, except for one specific value of alpha, which corresponds to the ground state. And this is alpha equal to n, which indeed corresponds to the minimal possible energy. So this brings us back to a problem of matrices, and then what we also discussed were properties in the framework of random matrix theory of this type of matrices, which are usually called spiked GOE matrices, where this is the spike and this is the GOE. And we discussed that there is this transition. So the parameter that you can tune here is the so-called signal-to-noise ratio. So it's the ratio between the strength of this perturbation, R, and sigma, which measures the size of the fluctuations of the entries of your matrix. And we saw that there is a transition when this signal-to-noise ratio is equal to 1. So if you look at values where R over sigma is smaller than 1, so the signal is too weak, you look at the spectrum of the matrix, and essentially you do not see any signature of the fact that the signal is there. So you find exactly the same spectrum that you would have in absence of the signal. So this means that you are restricting to these GOE matrices, and you find that the eigenvalues are distributed according to this density, which is the semicircle. You ask, what is the maximal eigenvalue that you're interested in because you want to understand the properties of the ground state, and you find that the maximal eigenvalue is precisely here, so at the edge of the semicircle. And then you ask, what is the projection of the eigenvector associated to this eigenvalue in this special direction W, which is the scaled version of my signal. So this W here is normalized to 1. And the idea is that in this whole region, again, this is exactly the same that you would get when R is equal to 0, so you find that the overlap is 0. So the two vectors are orthogonal, and this is actually true for all the eigenvectors of the matrix, not just the one associated with the largest eigenvalue. And on the other hand, if you go above this transition, you start seeing signatures of the fact that the perturbation is there. And this signature is given by the emergence of this isolated eigenvalue to the right of the semicircle. So this eigenvalue, as people say, detaches from the bulk of the eigenvalue density. It takes this precise form, so it's equal to sigma square over r plus r. And if you look at the eigenvector, which is associated to this eigenvalue, you see that now you have this eigenvector starts aligning with the special direction of the perturbation, which is given by W. Okay, so this is what we said yesterday. Now, let me add somehow one more ingredient to this. So, as you understood, all of this reasoning was precisely and exactly in the limit of the size of the matrix going to infinity. So that's the limit where you can define precisely this transition here. But in some settings, you're also interested about, let's say, finite n fluctuations. So now you can think of situations in which your size of the matrix n is very, very large, but it is not exactly infinite. So you are infinite size. And in that case, what you expect is that this transition somehow becomes a crossover. So if you are critical, of course, which is this point, is defined only in the limit n going to infinity. If you keep n finite but large, there will be a window around this asymptotic value where somehow things look as if you are at the critical point. And this window, so you look at references which are somehow in the notes, you can estimate that this window scales as a power of n, and the power is 1 over n to the 1/3. So as soon as you are away from this critical window, you enter into what you can call the subcritical regime or the supercritical regime. Now, what I'd like to add with respect to what we said yesterday are some considerations about finite n fluctuations of this maximal eigenvalue. That is, once more, something we are particularly interested in, keeping in mind this inference interpretation. So in this framework, so for this type of matrices, you can actually derive what is, if you keep n finite, what is the distribution of this maximal eigenvalue around the typical value. So we saw and we said that all these things are somehow self-averaging. So when n goes to infinity, the maximal eigenvalue takes a fixed value, which is either 2 sigma here and coinciding with this expression in there. But when n is finite, you will have fluctuations around. So what you can do is, let's estimate how fast these fluctuations decay, so how fast the distribution shrinks around the typical value. And also you can ask what is the shape of this distribution. And this is something that for these random matrix problems you can work out quite precisely. So if you are in the subcritical regime, the idea is that the distribution of this eigenvalue is once more exactly that you expect when r is equal to 0. And more precisely, there is a typical value, which is 2 sigma, and then you have these fluctuations around 2 sigma that decay with a precise power that happens to be n to the minus 2/3. So this goes to 0 when n goes to infinity, but when n is large and finite, you will see these fluctuations on this scale. And what is the distribution here? So the distribution is something that is quite well known in this framework of GOE and more general random matrices. It is the so-called Tracy-Widom distribution that is actually something that is pretty universal. So you see this distribution appearing in many settings. So some of you may have worked on KPZ physics, and this is the same type of scaling and exponents and distributions that you have there. Now, if you go instead in the regime where R is sufficiently large, so you somehow expect to see this eigenvalue that emerges, you actually have also a transition, a crossover, actually transition in the type of fluctuations that you have around this maximal eigenvalue, which become somehow more standard. So they become, in this phase, Gaussian fluctuations. So they decay, as you usually expect, with an exponent which is 1/2, and the distribution that you put here is no longer Tracy-Widom, but it is a Gaussian distribution. And this will be somehow some ingredient, in particular this exponent here, that will be somehow important if you want to reason about the dynamics of this system. Okay, so this was a little bit the summary. Are there any question, comment? So there is, you have to, okay, you have a window which, actually you have a scaling variable here, which is n to the minus 1/3 r minus r critical, where of course things are, it's somehow continuous. You can see there's a plot in the notes where you can see really the crossover between the Gaussian and the Tracy-Widow. And the plot is taken from a paper, okay, you see the reference. Okay. So at finite n, you see this continuously. You see this continuously. Okay, so having all this information, we can now go back to our inference problem. So if you remember, we had stated 3 questions, which were questions about recovery, landscape, and dynamics. So let's see how to translate all of this with respect to these questions. So the first one was about recovery, which was also, as we mentioned, equilibrium at t equal to 0, because of course now we are asking about the ground state of this energy landscape, which is the equilibrium configuration at 0 temperature. Now, what is the ground state? So the ground state, you see it here. It's the eigenvalue, is the maximal eigenvalue of this matrix, which is corresponding to the minimal energy, because I put a minus sign in here. And the question that you ask is, for which values of signal-to-noise ratio you have an overlap between your, yes, this is not a good location, an overlap between your ground state and the signal, which I can rewrite. Okay, let me take this square, so I can rewrite this as the overlap between the eigenvector, which corresponds to the ground state, which is un in my notation, with the normalized vector w. So this will be un dot w to the power 2. And what you wanted to say is that you can recover information on the signal whenever, in the limit n going to infinity, this converges to some finite quantity, which is different from 0. And now here you go back to this transition, and you realize that this happens precisely as you hit this critical point, because when you hit and go above this critical point, you start having an overlap which is non-zero with your signal. So you will have a continuous transition here at this critical value of r, which is equal to sigma, such that this overlap is 0 below this critical value, and then it starts growing and it converges to 1 when r goes to infinity. So I'm basically plotting this function here. Okay, and this point is precisely what you were asking for. So this is what you call your recovery threshold. And what this is telling you is that if you try to estimate your signal with maximum likelihood, if you are down here, your estimation is essentially impossible. So even if you are so good that you find immediately the ground state, this ground state is uncorrelated to the vector that you're interested in, so you cannot solve your inference problem. Whereas if you go above this critical value, your estimator is giving you information, so the problem is not impossible, it's solvable. Okay, so this is it for question 1. Now question 2 was more about the landscape, so about other stationary points which are in energy above the ground state. And this is again an information that you have, because you know that the energies of these stationary points are described in the limit n going to infinity by this density of eigenvalues. So here what you can do is to introduce a quantity, so let me call n epsilon this quantity. And this will be the number of stationary points that I labeled as alpha when n is finite, with an energy density which coincides with the parameter that I'm looking at. Okay. Now, when n becomes large, the number of stationary points with that energy density becomes proportional to the number of eigenvalues of your matrix, which have an eigenvalue which is equal to minus twice the energy density that you're looking at. And this is a quantity which is, in fact, self-averaging. So you can see that this n here is self-averaging because this density, if you remember, is self-averaging. And if I normalize it by 2n, so this is a quantity that will scale with n, of course, because n is the number of eigenvalues of the matrix. If I know, actually 2n is the number of stationary points because of this symmetry coming from the fact that the function is quadratic. So let me normalize this by 2n, and what I can show is that the limit of this quantity, which is a random variable at finite n, actually converges to the limit of the average of this quantity. And this is given by my density evaluated at minus 2 epsilon, or 2 epsilon because the density is symmetric. So here in this, let's say, framework where I normalize by 2n, I'm essentially neglecting contributions that come from the isolated eigenvalue. I'm just looking at the rest of the remaining stationary points. And you can plot what is their number asymptotically divided by 2n, and you have exactly the same picture as for the semicircle. There is just a factor of 2 of difference, so this will be sigma and this will be minus sigma. Now you're taking n to infinity, so now you can, we have the information about the energy, we can now ask about the stability. So when the size of your matrix goes to infinity, let's say this quantity alpha, which was labeling your eigenvalues, you can somehow consider it as a continuous variable in this limit. And what you see is that in the region which corresponds to what people call the bulk of the eigenvalue density, you essentially expect this index k, so alpha here will be proportional to n. You can scale it as n times some number. And so the index associated to this stationary point will be extensive in n. So this is what you call, so if you are here in the bulk, you have saddles. And these are saddles of extensive index. So the index scales with the size of your matrix. And this is true for the bulk. Now, if you are down here, so this is true all along this curve, when you reach the edge of your eigenvalue density, then with this scaling, everything is concentrating, so the density goes to 0. But you have some eigenvalues which accumulate in there, and these are the eigenvalues which are right above, let's say, the ground state, or if the ground state is an isolated eigenvalue, the second largest eigenvalue. And these are actually saddles with index that is intensive, so that you expect not to scale with n. Or let's say order 1 in n. Okay. And somehow the crucial information that you have here, that you already understood at that level, is that this is a landscape that is simple in the sense that you do not have all this multiplicity of local minima that you call glassiness and that you expect to be a problem for optimization dynamics. So if you think about now optimizing with simple algorithms these landscapes, what you expect is that if you remember my classifications between a hard and easy problem, this will not be a hard problem. So optimization will not require timescales which are exponentially large in the size of your matrix. Even though this doesn't mean that the dynamics is not interesting, and actually the dynamics of this model is particularly interesting, and it is also nice because you can say a lot of things about it using precisely these ideas and these results of random matrix theory. So now I'll try to very briefly give you an idea of what are results that people found for a dynamical optimization with the simplest possible algorithm that you can think of, that is this gradient descent or Langevin in the limit of a very small noise. I'll try to be brief. Let's see how this works. So question number 3 was about algorithms or dynamics. And the idea is obviously the following. So you are on your sphere. Somewhere you have your signal, and you put it here. You start from some initial condition. So let me choose my initial condition for the dynamics to be random. So I sample it uniformly from the sphere. So question now is, where do you expect this random initial condition to be? If you think about the sphere exactly, so very likely, because you are in high dimension, your initial condition will be somewhere here. And then I look at the dynamics where this evolves, so I follow the gradient. Of course, I want to stay on the sphere, so I follow the gradient, which is restricted to the sphere, and then in principle, if you want, you can add this noise, and I will consider t going to 0. And also the noise should be on the sphere. And not kick you out. Yes, 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 no. You don't want to be kicked out, yes. Okay, so now, let's say in general, if you have Langevin dynamics, you have a temperature, what you expect is that Langevin dynamics brings you to equilibrium, and if temperature is 0, the equilibrium configuration will be, as we saw, the ground state. So you would somehow expect that when time goes to infinity, the configuration that you reach is your ground state, which is one among the 2 possible configurations that you have on the sphere. Now, the point here, so I wanted just to mention this, is that, of course, you're interested in this large time limit, but you also have another limit here that you are taking when you do this consideration, which is the limit of n being large. So you may wonder, how do you take these 2 limits? So do you have to take them together? Do you have to take one first and the other afterwards? And actually, depending on what you do, you will see that you're able to study different regimes of the dynamics. So there is one way to proceed, or let's say the first thing that one can do to address these dynamical problems is to study the dynamics in a mean field regime. And this brings you to this framework of dynamical mean field theory equations that were discussed yesterday in the talk by Pierfrancesco for these problems of learning. So mean field here means that essentially you choose the order of limits in such a way that you first take n going to infinity, and then you take the large time limit. Okay. Now, it happens that this is a regime of the dynamics that one can study also in the more complicated setting of landscapes that we will see in part 2. Because if you take the limit in this way, there are some nice features, which in general occurs when you look, for example, at fully connected systems. So this energy landscape is fully connected in the sense that if you interpret the structure, now I erased it, but if you interpret but I remember it was here, so try to use your photographic memory. Now, okay, so you have the energy was sum jij, sij, so you can interpret this as an interaction between the components of your configuration vector, and you see that you have all-to-all interactions, so it is fully connected in this sense. So in general, these Largan dynamics for fully connected systems have some nice features. So let me very briefly mention those. Yes. Yes, so I want to, yeah. Yes, so I want to think of this as a process where I let a little bit of noise to, let's say, yes, and then I switch it slowly to 0 so that I converge. Here it's, this limit is in general continuous, so you don't worry too much. So the idea is that, okay, if you do just gradient descent, it may happen that you slowly converge to some saddle, and a saddle is already trapping, because if you just have this term, the dynamics the variation is 0, so this is an attractor of this gradient descent dynamics. So I want to allow for a little bit of noisy fluctuations to avoid this type of things, and then you go down in this energy landscape, and then once you equilibrate, you somehow try to kill the noise. Yes, or you can do directly Langevin with an epsilon of noise, and then you kill it. If you imagine that you reach. So these are models, also the one that I will talk later, that have also a landscape that is very continuous in temperature. So what is a minimum of the energy, in general, stays a minimum of your free energy if you increase temperature a little bit. This is not the case that Silvio was discussing, for models that Silvio was discussing yesterday, but for the models that I will describe. Yes, I mean, in general, you could worry about this, but this is not the case here. So, okay. So what are the properties that you find if you take this limit? So the first one is that you recover this self-averagingness at the level of the dynamics. So you find that there are, so now you have trajectories. And these trajectories, well, fluctuate. There are two sources of noise. So one comes from the fact that you have a landscape which is random, so you can change the realization of your landscape, and you think about averaging with respect to these realizations. And then in principle, you also have the noise of the dynamics, which makes, for fixed landscape, your trajectory stochastic. So the idea is that if you take this limit, you recover something that is self-averaging. So there are some properties of the dynamics, of the trajectories. For example, the energy itself along your dynamics, so which I will call E of t, which is your energy function evaluated along your trajectory, which becomes self-averaging. Which again means that you look at this Largan limit, you have something which fluctuates at finite n. Let me take the energy density, and this actually converges to the average, where now this is an average with respect to the landscape and also with respect to the noise of your dynamics. So let me call it epsilon of t. And there are other properties that you may look at. For example, you can look at correlation functions that also appeared yesterday. So this is a one-point function in time. Correlation functions are two-point function in times, which at finite n are just written as a sum over all the components of your configuration vector of the corresponding component evaluated at time t and the component evaluated at a different time t prime. So this quantity becomes self-averaging, and moreover, you can derive equation which are closed equation for 1 and 2 point functions in time. And these are the MFT equations that were discussed yesterday. So you will have closed equations which are expressed in terms of the correlation function, the energy, the response function, which also emerges, which is a different 2-point function. You have these equations. You can try to solve these equations, study the limit of t large, and you will have somehow the dynamics in the mean field framework. Now, of course, this is strictly for n going to infinity. Why n going to infinity? Well, you see in the formalism, when you derive these equations, that these are obtained as some saddle point approximation that, of course, holds true in the limit in which n is large. So you have this derivation as a structure which is relying on the fact that you are asymptotic at large n. Now, the second regime that you may be interested in is a regime where n is finite, but still large. And this is, in general, for this type of problems, something that is quite difficult to study. So and partially, this is due to the fact that when n is finite, somehow things remain distributed, as we saw for the largest eigenvalue. So there is a limit when n goes to infinity, but if you keep n finite, there is a distribution around the typical value. So you expect that also here, all this quantity will still be distributed, and there is not this property of self-averaging. You cannot derive equations because you do not have this n to infinity limit. So things are more complicated in this case. But the nice thing, so the reason why I wanted to discuss quadratic landscape first, is that in this particular case, you can actually say something also about these dynamics. So for this case, you can say something, and you can say something because, again, you map this into a problem of random matrix theory, and you know a lot about this type of random matrices, and this helps. Is the distinction more or less clear? Okay. Okay, now let me summarize very briefly what you find if you go back to our case in these two frameworks. And now I should be brief, so let me see what I should say. Okay, first of all, what are simplifications that occur for our quadratic landscape? So let me introduce a quantity, which is a quantity which measures in time how far you are from the state that you want to reach, ideally at t equal to infinity, that is the ground state. So I will try to measure how far we are in terms of energy. So I will introduce a quantity which is the excess energy, that is the difference between the energy along my trajectory at time t, which may depend on n, because now I am at finite n, minus the ground state. Now, in this model, I have no time to go through this, but the idea is that you can write down exactly an expression for this energy difference. And what you find is that this will be a function. So everything is in this model is encoded in the spectrum of the matrix M. So not surprisingly, this will be a function of, let's say, differences between eigenvalues of your matrix M. And in particular, if you look at how this function behaves when time is large, there will be one particular difference which dominates. So you see that the behavior of this function, you can write it in this way, where Gn is actually the gap between the largest eigenvalue of your matrix and the second largest eigenvalue. So in my notation, Gn will be lambda n minus 1. And here I am at n finite, and I have eigenvalues which I can label in this way. Now, this type of structure somehow tells you that there is a natural timescale here, which is the timescale which separates a regime where you do not, essentially, you do not see that your system is finite from a regime where you start seeing that you have a discrete spectrum, for example. And this timescale that I will call tau, I don't know, I call it dynamical crossover. This timescale is what? So it is the timescale where this object is of order 1, so it will be of the order of 1 over the gap. Okay, so how does this gap scale with n? So before I gave you this, that I erased again, but somehow we discussed what is the scaling of fluctuations of the largest eigenvalue in the two regimes, subcritical and supercritical. And the idea is that essentially the same type of exponent you have also for the scaling of the gap. So the distance between the largest eigenvalue and the second one has a scaling in n, which is of the same order as the fluctuations of the largest eigenvalue itself. So this means that we can expect that this, I didn't show you, but you essentially, you have, the idea is that this type of dynamics, in our case, so you can diagonalize it. So let me say that I change my basis, so I define component as alpha as my vector S, scalar product with one eigenvector. And then my dynamics, I can write it as dSA over dt equals to, I have a minus. Then the gradient was what? Was the matrix time S. The matrix, I'm diagonalizing it, so here I will have, so you have to remember, so you have lambda alpha minus the Lagrange multiplier that now depends on time because you want to keep your trajectory on the sphere at all times, times S alpha. Plus eventually the noise, which is isotropic, you can also rotate it. So this looks like very simple dynamics, so it looks, there is a linear term. Now the only difficulty is that all these modes are coupled because you have this Lagrange multiplier that couples the modes. But you can nevertheless integrate these dynamics, so you have really explicit expressions for your energy, and then you plug them here, you derive this form, and then you get what is the largest time term that remains. So now we were here, so what is the scaling of the gap? So in the case in which now you have this transition, so let me go in the case where you are below, let's say, the critical point and away from the critical region. So this is the subcritical regime. Then question, so which power of n should I put here if I am in this regime? Yes, not minus, because I'm looking at times, so it's 1 over. So this is n to the, not 1/3 actually, but 2/3. So the idea is that what controls these fluctuations is really the scale of fluctuations of eigenvalues at the edge, which is the same scale of fluctuations of the maximal eigenvalue itself, and this was decaying as n to the minus 2/3. Okay? Is this clear to everybody? Okay. So here you expect n to the 2/3. If you are above this critical region, now your maximal eigenvalue is detaching from the bulk. So let me draw what was the situation here. So below the critical region, the maximal eigenvalue was here at the edge, and it was fluctuating with something of the order of minus 2/3. If you go above the transition, you have this maximal eigenvalue that detaches. It has its own fluctuations, which are 1 over n square root. But now you're looking at the gap. And the gap now you see that it is of order 1, because the distance between the maximal eigenvalue and the second one now becomes of order 1 in n. So before they were both concentrating on a scale, so the gap was going to 0 when n goes to infinity. They are all concentrating here, and the right scale is this. Now your system becomes gapped, and g will be of the order of 1. So in principle here you would put n to the 0, and actually the right crossover time here is a log of n. And you can find references on this. This is dynamics that has been studied. So what does this crossover timescale tell you? Well, it tells you that as soon as you look at times which are much smaller than this timescale, your dynamics is well described by this mean field limit. So these timescales are short enough so that it looks as if your system is infinite and you do not see this finite n. So this is where the MFT is good. And then if you look at larger timescale, you really have to look at finite n dynamics. Okay, so this is A and this is B. Okay. So let me just mention in 2 words what you find in these 2 cases. So let's look first at what you find as a result of your DMFT. So what you can do is you go back to this, and now you take n going to infinity first. So you look at the limit of, no, sorry, this quantity when n goes to infinity. So this will become self-averaging, so it's also the limit of the average of this quantity. You then look at how this behaves by solving the equations when time becomes large. And you basically see that in the phase where the system behaves as if the signal is not there, actually the behavior is a bit the same here, but let me try to be more precise. So if you are in the, what I call the subcritical regime, then you can work out that this decays to 0. So you are converging to the right energy density within these timescales, but it decays to 0 actually quite slowly, so people have worked out what is the asymptotic behavior of this, and you find that there is an algebraic decay to 0. Now below, if I define my crossover like this, below you have essentially the same behavior, so this is actually above. Except that in fact, so here I was defining this as the difference in energy between the energy at time t and the ground state. And if you are below this logarithmic timescales, you do not really see the ground state here, so you basically converge over these timescales and with the slow decays to the edge of your semicircle. So your ground state corresponds to the isolated eigenvalue, which is down here. But here you are essentially describing a dynamics which reaches only this point here. So I should put here the difference between, so I think this is minus sigma minus the ground state, where now the ground state is the one associated to the isolated eigenvalue. But in any case, in this, let's say, short time regime, what you see is that you have a slow decay. And actually, in these timescales, you can look, for example, at how correlation functions behave, and you find that the system is essentially always out of equilibrium. So you may look at how these correlation functions behave, and you see that this doesn't become time translation invariant, but it actually shows features of slow dynamics that you usually have in glasses, like aging. So I will not go into that. Maybe some other courses will. But the idea of aging is that you have a system that essentially becomes slower and slower as the dynamics proceeds in time. So the system is, if you want, less and less prone to change its configuration as it becomes older. So this is the idea of aging. And you can give a landscape interpretation to this. So the idea is that, so you go back to this picture here. So let me draw it as a function of the energy. So this will be supposedly, if you are in the supercritical regime, the ground state is here, otherwise it is here. This is 0, this is minus sigma, and this is sigma. So what's happening over these timescales is that you start from random initial conditions. So typically you are at energies that are in the center of the band, where you have most of your configurations. And then what the system is doing is to moving down along this curve and asymptotically reaching this edge in here, which corresponds to the good energy density in the subcritical regime. And why the dynamics becomes slower and slower, when one way that you can interpret this is that you are moving in a landscape which has all these saddles. And remember that the index of the saddles is decreasing as you go along this curve. So this means that you have all these regions where to go down you have to find negative directions, but negative directions are less and less, so the dynamics becomes progressively slower, and this is one geometrical way to somehow interpret why you have this out of equilibrium aging dynamics. Okay, this is first regime, and now what I just want to mention is that you can go beyond this and look at what happens at very large timescales. So the first thing that you can say is that, well, this difference in general is not, you lose this property of being self-averaging, so it's not obvious that the average describes completely the statistics of your dynamics, but let's still consider the average in here. Actually, I should not do this, so let me look at this excess energy at a function of t. And now I am at finite n, so I can go back to this expression. And I can use the fact that my excess energy now depends on these timescales on the statistics of the gap. So let me take the case first, r equal to 0, so where you have just the GOE. So here, the idea is that for these GOE matrices, you know really a lot of things about the statistics of the gap, in the sense that you know the full distribution of this quantity. So you know what is the distribution, so you maybe rescale it. The gap is of order, so you have to blow it up like this. And this is known. Now the average of this quantity will be essentially the average of this expression that if you know the distribution of Gn, you can compute. So you do this, and what you find is that in this case, so maybe I'll write it here, you can really work out, because you have this information, you can see that when t becomes large, this thing behaves as another function, which is a scaling function of time that you know explicitly, that I am not writing it down. Actually, I can write down what are the limits of this function, so you know that f0 of x will go like this. So you have matching when x goes to 0, and this is consistent because it means that you're looking at times which are smaller than the scale that you have. And if you look at x very large, actually you still have algebraic decay, but a little bit faster. I think it's x to the cube, I think. Yes. And this is something that you expect somehow for the whole subcritical regime. So as r equal to 0 in the subcritical. Now, if you are in the other regime where you instead start having this, you have this ground state which is separated from the rest, then you expect a different dynamics. So now you look at very large time scales. So your gradient descent has brought you down these landscapes made of saddles, and at these time scales it realizes that there is this ground state there. This ground state is isolated, is a minimum. So how does one expect the decay to go? If you are in a region of the landscape which now is convex, there is just one minimum and you need to equilibrate. Exactly. So here it will be exponential. I write it sloppily, but it's exponential, and there is a dependence on the gap here, and the gap is the difference between the ground state and the edge. Okay, so this was maybe a bit sketchy, but the idea is that in general, studying this regime of the dynamics is a very difficult problem, and here this is an example where you can actually say a lot of things again because you know things from randometrics theory. Okay, so if this is fine, then this somehow concludes part one, and now very briefly I'd like to try to set the stage for the second part, which I somehow introduce with a little bit the same framework, so the same motivation of looking at inference problem, but now the problem will be a little bit more complicated and the landscape will somehow look different. Okay, so this is part two. Okay, part two will be about an inference problem that is no longer easy, but it is hard. So the motivation is, again, to look at the noising problems, except that now the object that you want to denoise is more complicated than a matrix. For example, it has more indices than a matrix, and it is, therefore, some tensor. So with the same notation as above, I have an observation. So I introduce a number p, which is larger or equal to 3. So whatever we have discussed so far corresponds to p equal 2. And I introduce a tensor which I observe, which has p components, which is again the sum of one tensor which is random, with entries that are Gaussian and independent up to symmetry, plus a signal term which has basically the same structure as before, except that I have a higher nonlinearity here, so I have the signal dot s divided by n to the power p. So this is again the signal, and this is my noise or randomness, which is symmetric, which means that if I permute the order of these indices, the value of the coupling is the same. It's Gaussian. Again, the average is 0. And the variance is, now you let me normalize it a bit differently. So before we add this coupling sigma, let me add here a sigma tilde and a p factorial in front, which simplifies a bit the notation. And then you have here a different power in n, which is p minus 1. Okay, so now I go a bit fast because it's the same logic as before. So you introduce again this maximum likelihood estimator. And you find that this coincides again with the ground state of a high-dimensional landscape, again on the sphere, which has now this form. So I have the random part, which is the contraction of my tensor. So now I sum here. So there is a bit, one has to decide whether to sum over all entries or only on non-repeating indices. So let me sum over non-repeating indices with this convention. So you have the contraction of your random tensor with the vector S. And then you have, sorry, this is wrong. Sorry, here you should have R over N, and then you have the tensor that you build out of the vector. I was already contracting it with S, but no, here you have the rank 1 tensor that you build out of your signal vector V. Okay, so the random part gives you this, and then you have what I was writing there before. So you have the part which comes from the signal that is the scalar product to the power p. Okay, so again, you ask the same questions as before. So you are interested not only on the ground state, but also on all the stationary points. So what you can do is to try to do the same calculation that we did for p equal 2. So you implement your spherical constraint by adding here the same Lagrange multiplier Si2 minus n. You define again your stationary points as pairs S star lambda star, which are such that the derivative of this landscape with the Lagrange multiplier with respect to each component evaluated at this point is 0, and then you also have the derivative with respect to the multiplier itself. So you will have similar equation as before, and you can use the same strategy to work out what is the expression of the Lagrange multiplier, and as before, you will find that lambda star at a given configuration, you can write it, so this is really as for p equal to 2. This object here will be essentially the gradient of your function in the direction of s with a minus divided by n. And since you have a function which is homogeneous, so which has the same power of s which appears in both terms, what you realize is that if you take the gradient and then you multiply again by s, you recover an expression that is proportional to the energy itself. So this, as in the case p equal to 2, will be equal to minus p times the energy density at the configuration S star. I hope I'm fine with the signs. Yes. Now this is like the quadratic case, but of course there is a difference, and the difference is that now the first set of equations is non-linear anymore because your landscape has a higher degree. So you can no longer map this to a problem of diagonalization of matrices. Nevertheless, you still want to say something about the structure of this landscape, so let me introduce the same quantity that I was introducing before, so this number of stationary points, and now I try to track both the energy density but also the overlap Q, so the value of the overlap Q of the stationary point that I'm looking at with a signal. So this will be the number of stationary points S star with energy density epsilon n such that the overlap with the signal is equal to Q. Okay, now the idea is that you have a more complicated landscape here, and the scaling with n of this quantity will be quite different with respect to what you have in the quadratic case. So in the quadratic case, what we just said just before is that this number, so we were not looking specifically at the overlap with the signal, we were just looking at the number as a function of the energy density, but the idea was that this number was of the order of n, and it was a self-averaging random variable. So if I look at this quantity divided by 2n, the distribution in the limit n going to infinity concentrates around the typical value that is given by my semicircular law. Now, if you go to higher values of p, both these statements are no longer true. So the first thing that you see is that now your landscape is much, much more non-convex. It's much, much more rugged. So the number of stationary points that you have has a scaling that is no longer linear in n, but it is exponential in n. And this is a random variable which is not self-averaging. In general, actually. Okay. So now I will introduce some quantities that you can use to characterize the behavior of this random variable when n is large. So the idea that the scaling is like this, I can rephrase it by introducing another random variable. So I rewrite this as e to the n times some quantity, which is random, that I call sigma. And this more or less corresponds to saying that when n becomes large, the distribution of this quantity, so you're scaling this in the appropriate way, so the distribution of this quantity remains bounded, it remains of order 1, essentially. And actually, you know something more. So you know that this quantity itself is self-averaging. So I can look at the limit of sigma, that is log of n divided by n. And this will converge to this average here. That I call sigma infinity. And then I will drop this infinity in the following. And this is what I call the complexity of the landscape. It's a definition. No, this will not be. What you have to look at is the log of that random variable. Ah, sorry. There's a note. Yes, indeed. It's important. I'm a bit sleepy this morning. Okay, so you want to compute this. So the fact that, what is this controlling? So what is this telling you is essentially what is the behavior when n is large of the typical value of this number here. So let me call this n typical. So this statement is telling you that if you're interested in the typical value of this random variable, now the typical value is in general the value which is the most probable, where the distribution peaks, the scaling of this typical value will be controlled by this quantity. So it will be of the order of e to the n times my complexity, and if you have finite n, you have corrections which are subleading in n. Now, in general, what happens for these quantities that have this scaling is that when n is large, the typical value is not, in general, coinciding with another quantity that you can compute, which is the average value. So the average value will be, in general, something that scales differently with n. And its scaling will be controlled by another function, which I will call SA, and A stands for annealed. And SA is essentially the limit n going to infinity of the log of the average of n divided by n. So these two quantities are different, and what you can argue quite easily is that this annealed complexity, so let me call it annealed complexity, and let me call it, this is the complexity of the landscape, or sometimes called the quenched complexity. So the idea is that if you compute this function, in general, you will find that this function is larger than the quantity that you're interested in. So you have a bound which tells you that the annealed function is in general larger than the quench complexity. Which is something that one can understand a bit intuitively. So the idea is that when you look at typical values, you are looking at what happens so you have your systems, you have maybe many realizations, so you do many experiments where you generate many landscapes, you count the number of stationary points, so each of you will have its own landscape, so it will have its own number of stationary points, and I'm interested in at what happens most of the cases. So for most of the experiments, assume that we are very many, n is very large, I want to understand what happens with the largest probability, and this will be the typical number of stationary points. Now, there will be some of you, so maybe few, that will have very special realizations of the landscape where the number of typical points there is extremely large or extremely small. And this will happen with very small probability, so with a probability which decays to 0 when n goes to infinity. The point is that when you compute these averages, this probability, so you're computing an average of something which scale exponentially with n. The probability of observing something special maybe decay, but also exponentially with n. So you have some competition in this calculation of the average. And this competition will make it so that the average quantity will actually be dominated likely by the very few realizations among you that have a very large number of stationary points. So the idea is that, in general, if you have this mismatch between typical and average value, you find that the average number of stationary points is much larger than the typical one, which is what I'm saying here, because it will be dominated by those special realizations that are very, very rare, but where you have a huge number, exponentially larger number of stationary points. So when this happens, these two quantities are different, and the reason why I introduced this is that I mentioned that we are actually interested in computing this one, but what I will do in the following is actually discuss very briefly the calculation of this quantity here. And the reason for this is that computing this quantity is in general much simpler than computing this quantity. And I will now briefly tell you what you have to do to compute this, and you will understand why the other one is easier. Sorry? Well, what you can think of, so, okay, let's look at the average. So the average of these, let me use a short notation. So we will have roughly an integral over dn of n, and then the probability to observe a given number of stationary points. Now, the idea is that in the problem we are looking at now, this is a quantity which grows as e to the n times something in general. And the probability can take some large deviation form, so you will have a most probable value, and then you will have some decay that in general is exponential. So this will go like e to the minus n times something. So when you compute the typical value, what you are computing is instead dn log of n times p n. So if you do this calculation, so you take the log of this quantity, this is no longer exponential, you bring this down, and then what wins is the probability. So if this probability becomes exponentially small, you kill all those realizations and you concentrate on those realizations that have a probability of order 1. And these are the typical realizations. Here you in general have a competition between these two. So you can think in this framework you can do some sort of saddle points, but the saddle point will be shifted by this quantity. Sorry, by this quantity. It will not be, it will be in a different point with respect to this. So this is why. Now, why p equal to 2 doesn't work? Because you do not have this. Well, one way you can think of is that, indeed, quadratic landscapes are simple enough that they encode this diagonalization problem. Your matrix is n by n, and there is nothing more than you cannot have more than n critical points. In general. So what do you mean computing at temperature? So now to rephrase this in temperature, you would say, okay, instead of the energy, I take a free energy, and then I try to compute stationary points of this free energy. Yes, but I mean, if you are at the same, okay, so let me say one thing, and then I will go back to what you said that I think I didn't get properly. But let's say this inequality, in a way, is just coming from the fact that you are looking at the log, and it is an identity that is due to the convexity of the log. So one way to see this is you have the log looks something like this. So you are, let's say that you take 2 points. This is how I remind me which one is larger. So the log has this convexity. So this point here will be, so this is the average, no, wait. Okay. This is what? This is the function evaluated at the average, so the log evaluated at the average between these 2 points, and this is the average of the log. And then because you have this convexity, you have this inequality here that holds. I hope I got it right, but okay, the wording maybe was not right, but you should get it right. So, I mean, in a way, this is just encoded in the function that you're looking at. Now, I'm not sure this is what you were commenting on. Yes. But what it means for you specify by temperature? For me, it means that I take a free energy instead of the energy landscape, and then I do the calculation of the number of, let's say, minimum of this free energy in the 2 different ways. And then you need to recover this. Yes. Yes. What do you define as a yield there? How do you define computing a yield? That you compute in the 2 different ways, annealed and quenched. Okay, maybe we pause, and I have to understand what you're saying a bit better. Which one? This one? No, here I'm just sketching. Okay, so in general, n typical will be what? There is, okay, my n are all the same, so this is curly n. And yes, there is an exponential. Of course. I mean, I'm expressing this average, and then n will be the exponential of that average. Okay. Thank you. Okay, so we were here. So what do you do in general to compute this quench complexity? So what you have to do is to compute the average of a log. And the way people usually do this is by using the replica trick. Which in this context is just a way to write the log as, so let's assume that you have a quantity x, which is positive, and I want to write the log as some limit. So let me introduce some number that I call m, that I want to send to 0, and then I have the power of this quantity to the m minus 1 divided by m. This is just an identity, so if you want to see this, what you can do is you take this x to the m, you write it as e to the m log x, and then you do an expansion around m equal to 0, you take the limit, and you see that the only thing that remains is the log of x. So in this context, this means that to get this S infinity, what you have to do is to do a double limit. So you have n going to infinity, and then you have m going to 0, and then you have the average of the log divided by n, but the average of the log, I write it like this. So I will have the average of curly n to the power m minus 1 divided by m times m. And the reason why this is useful is that, in general, you don't know how to compute. So this random variable contains the energy that you want to average over, but taking the log is complicated. It is much easier to compute moments of this random variable, where you just take products of n, and then you average the product. So in this way, you are rewriting, you're mapping the problem of computing averages of logs in the problem of computing moments of, moments are just averages of n to some power, moments of your random variable. And then you have to use, so in general, moments are defined for m, which is an integer, 1, 2, 3, 4, and so on. And to get the log, you have to do this analytic continuation, so to compute the expression for general values of m, and then take the limit m going to 0 and see what remains in this limit. But somehow the idea is that this is a bit more complicated because you have to go through this calculation of moments and then takes the limit. Whereas if you look at this annealed complexity, the only thing that you have to do is to compute the first moment, because this is just obtained as the log of the average, which is the first moment. So you just compute the first moment, and then you have the answer for your complexity. So what I'd like to do, starting in 5 minutes and then next, is just to tell you a little bit how you do the calculation of this average, and then I will show you results for our problem of the noising of tensors, which actually come from the quench calculation, but this is some of these results are actually already encoded in the annealed. So I just maybe take 5 minutes to introduce what you need to compute this average, and then we do the calculation after the break. Now, what you can use to do this calculation is the so-called Cargèse formula. So Cargèse formulas are counting formulas. So the idea is that you want to count the number of solutions of a given system of equations. So this system of equations may be random, so you want to count the average or some moments of the number of solutions of the system of equations. So to introduce how this works, let me start from a very simple example, which is non-random. So suppose that I have one function in one dimension in some interval. Maybe this function looks like this, and what I'm interested in is counting the number of points in this interval where my function takes a given value that I call y, and this should be a straight line, but okay. So in this example, I fix my y, and I see that I have 4 points which satisfy my condition. Now let me call n of y the number of solutions, so of points x such that f of x is equal to y. And I'll try to write down an expression for this number, so I'll do it in this way. So I have my interval a and b, and what I do is I scan all possible values of x, and I put a weight, so I put a delta function anytime I meet a value of x which satisfies my condition. So I write this number as the integral over ab over all my possible x's, and then I put a delta whenever x satisfies my condition, which means that x has to be equal to f to the minus 1 evaluated at y. Okay? Then in this formula there is an f to the minus 1, which I don't like, so let me make a change of variable inside the delta function. So I rewrite this delta function as delta of f of x minus y. But then I have to add something. What's missing? There is a Jacobian that comes from exactly, which is the first derivative. So it would be 1 over the absolute value of the derivative of this function, which is 1 over the absolute value of the derivative of f to the minus 1, which I can write as the reciprocal, it's equal to the absolute value of the derivative of f, basically. So the Jacobian that I need here is f prime of x. And if I do this in higher dimension, I will get essentially the same thing. So suppose now that my x is a vector in d dimension. Suppose that y is also a vector. And it is given by f1 up to fd. I ask the same question, so I just have to rewrite this in the I-dimensional version. So let me call the interval now in dimension d, let me call it I. So I will have the integral over all vector x that belong to this space. Now I have a lot of components for my function f. So here I can write it as the product I going from 1 to d of the delta of the corresponding component. And then I have the derivative, but now the derivative, so I have more variables and more components, so this derivative becomes a matrix. So what I have to do here is to put the absolute value of the determinant of this matrix, and this matrix is the matrix of derivatives of f of x with respect to fi of x with respect to xj, component ij. Okay. Okay, so now I think we can have coffee, and then we will start from there, and we'll compute this for the case that is interesting for us.